Section 1: The mathematical lock that protects the world. How modern cryptography secures the internet and why it depends on problems believed to be unsolvable. Every message sent across the internet, every bank transfer, medical record, private email, government communication, and encrypted video call rests on a single, fragile assumption that certain mathematical problems are effectively impossible to solve. Not unsolvable in theory, but unsolvable in practice, even for the fastest computers humanity has ever built. This assumption is not philosophical, it is mathematical, and it is the foundation of digital civilization. The modern internet is not secured by secrecy, it is secured by mathematical asymmetry. At its core lies the concept of a one-way function, a calculation that is easy to perform in one direction, but extraordinarily difficult to reverse without special information. Cryptography does not rely on hiding algorithms. Every major encryption system used today is public, peer-reviewed, and mathematically transparent. What protects your data is the belief that reversing these computations would take longer than the age of the universe. To understand why this matters, one must first understand what encryption actually does. When data is encrypted, it is transformed from readable information into structured randomness. This transformation is governed by mathematical algorithms and cryptographic keys. Anyone can encrypt data using a public key, but only the holder of the corresponding private key can decrypt it. This public-private key system is the backbone of secure digital communication. One of the most widely used systems enabling this security is public key cryptography, particularly schemes based on number theory. These systems exploit mathematical problems that are easy to compute in one direction, but extremely hard to reverse. The most famous of these is integer factorization. Multiplying two very large prime numbers together is trivial for a computer, but determining which two primes produce a given large composite number is computationally infeasible using classical algorithms. This is not a weakness, it is a deliberate design choice. Cryptographic systems such as RSA, Diffie-Hellman key exchange, and elliptic curve cryptography depend on this asymmetry. The security of the internet is therefore not protected by physical barriers or firewalls alone, but by the limits of computation itself. To appreciate the scale involved, consider the size of the numbers used. Modern encryption relies on keys that are hundreds or thousands of bits long. This corresponds to numbers so large that the total number of possible combinations exceeds the number of atoms in the observable universe. A brute force attack trying every possible key would require more energy and time than exists in cosmic history. This is why, for decades, cryptography has been considered safe. Classical computers, no matter how fast, are constrained by linear and polynomial scaling. Even the most powerful supercomputers cannot efficiently solve these underlying problems. The internet grew confident. Banks, militaries, hospitals, and governments built entire infrastructures on this assumption. But there is a subtle vulnerability hidden within this confidence. The security of cryptography does not depend on mathematics being unsolvable. It depends on mathematics being slow. If a new model of computation were to emerge, one that could solve these problems exponentially faster, the lock would fail. Not gradually, not partially, but catastrophically. This is where the story begins to shift. Cryptographers have long known that encryption is only as strong as the assumptions behind it. These assumptions are rooted in computational complexity theory, the study of which problems can be solved efficiently and which cannot. Problems like factoring large integers belong to a class that is believed to be hard for classical computers. But belief is not proof. There is no mathematical theorem that guarantees these problems cannot be solved efficiently, only decades of empirical evidence. For most of computing history, this distinction did not matter. All computers operated under the same physical principles: bits that are either 0 or 1, transistors that switch on or off, logic gates that follow deterministic rules. Progress meant faster clocks, smaller transistors, and more parallelism, but never a fundamentally different way of computing. That assumption, too, is about to break. Before exploring how, it is essential to understand how deeply encryption is embedded in everyday life. When you open a secure website, your browser initiates a cryptographic handshake. This handshake verifies the identity of the server, establishes a shared secret, and encrypts all subsequent communication. This process occurs in milliseconds, invisibly, billions of times per day. Every cryptocurrency transaction depends on cryptographic hashes and digital signatures. Every software update relies on cryptographic verification to prevent tampering. Every password stored securely is protected by mathematical functions designed to resist reversal. Even state secrets classified at the highest levels rely on encryption algorithms that assume certain mathematical problems cannot be solved efficiently. The Internet is not one system. It is an interlocking mesh of trust relationships enforced by cryptography. If that trust collapses, systems do not merely become vulnerable, they become meaningless. Imagine a world in which encrypted traffic can be decrypted retroactively, where stored communications, once thought secure, are suddenly readable, where digital signatures can be forged, identities impersonated, and financial systems manipulated invisibly. This is not a hypothetical scenario built on speculation. It is a logical consequence of breaking the mathematical assumptions underlying cryptography. And this is where the quantum secret begins to surface, not as science fiction, but as a concrete scientific possibility. The vulnerability is not that encryption is poorly designed. On the contrary, it is brilliantly designed for a classical universe. The threat emerges because the universe itself permits forms of computation that classical computers cannot exploit. Nature, at its most fundamental level, does not operate on bits. It operates on quantum states. For now, classical cryptography remains secure. No existing classical computer can break modern encryption at scale. But cryptographers are acutely aware that security is not defined by what is possible today, it is defined by what may become possible tomorrow. This awareness has led to a quiet but urgent question spreading through cybersecurity, intelligence agencies, and scientific institutions worldwide. What happens if the mathematical lock protecting the Internet is no longer slow? That question does not yet invoke quantum computers explicitly. But it sets the stage, because once computation itself changes, mathematics does not change but its difficulty does. Section 1 establishes a crucial truth. The Internet is secured not by invincibility, but by delay. Encryption assumes attackers cannot solve certain problems fast enough to matter. If that assumption fails, the digital world does not degrade gracefully, it breaks. In the next section, the documentary will step outside classical computation entirely and into the physics that makes a different kind of computer possible. Section 2 Enter quantum mechanics, when physics rewrites computation. Why the universe itself allows a radically different kind of computer. To understand how the Internet could be broken, one must step away from mathematics and into physics. Classical cryptography assumes that computation follows classical physical laws, deterministic, binary, and local. For decades, this assumption held true because every computer ever built operated within those constraints. But nature itself does not. At the most fundamental level, the universe does not process information in bits. It processes reality through quantum states that obey rules radically different from classical intuition. These rules do not merely allow faster computation, they permit entirely different categories of computation. Quantum mechanics emerged in the early 20th century as physicists attempted to explain phenomena that classical physics could not: blackbody radiation, atomic spectra, and the stability of atoms themselves. The resulting theory revealed a world that behaves probabilistically, where particles exist in multiple states simultaneously and influence one another instantaneously across distance. For decades, quantum mechanics remained confined to theoretical physics and experimental laboratories. It described electrons, photons, and atoms but not information. That changed when scientists realized that information itself is physical. If information is stored in physical systems, then the laws governing those systems determine how information can be processed. This realization led to a profound insight. A computer built from quantum systems would not merely be a faster classical computer. It would be a different computational entity altogether. Classical computers operate on bits. A bit is either a 0 or a 1. Every calculation, no matter how complex, reduces to sequences of these binary decisions. Even with massive parallelism, classical computers remain constrained by this binary structure. Problems that require exploring vast combinatorial spaces quickly become infeasible. Quantum systems, however, do not obey binary logic. A quantum bit or qubit exists in a superposition of states. It can represent 0 and 1 simultaneously, with probabilities defined by complex amplitudes. This is not metaphorical. It is a direct consequence of quantum physics. Superposition allows a quantum system to encode exponentially more information than a classical system of the same size, but this alone does not enable computation. The real power emerges when superposition is combined with quantum interference, a phenomenon in which probability amplitudes reinforce or cancel each other according to precise mathematical rules. This means a quantum computer does not try every possible solution randomly. It explores many possibilities simultaneously, then uses interference to amplify correct answers and suppress incorrect ones. Computation becomes a matter of shaping probability waves, not executing step-by-step logic. Another crucial property of quantum mechanics is entanglement. When particles become entangled, their states become inseparable, even across vast distances. Measuring one instantly determines the state of the other. This correlation is stronger than anything allowed in classical physics and has been experimentally verified countless times. Entanglement enables quantum systems to represent relationships between variables that classical systems cannot efficiently encode. In computational terms, it allows qubits to act as a unified system rather than independent units. This collective behavior is essential for solving certain classes of problems dramatically faster than classical computers. It is important to emphasize what quantum mechanics does not do. Quantum computers do not magically solve all problems faster. They do not violate causality or allow arbitrary speedups. Their power is highly specific, constrained by the structure of quantum algorithms and the nature of the problem being solved. This specificity is precisely why cryptographers are alarmed. The problems underlying modern encryption, such as integer factorization and discrete logarithms, have a very particular mathematical structure. For classical computers, these problems resist all known efficient algorithms, but quantum mechanics changes the computational landscape. It enables algorithms that exploit the structure of these problems in ways classical physics simply cannot. This is not speculation. In the 1990s, theoretical physicists and computer scientists began asking a dangerous question: if a computer were built using quantum mechanics, what problems could it solve efficiently? The answers were unsettling. Quantum computation was formalized through rigorous mathematical models. Researchers defined quantum logic gates, quantum circuits, and complexity classes. They proved that quantum computers could simulate classical computers efficiently but not vice versa. In other words, quantum computation strictly contains classical computation. This meant that quantum computers could, in principle, do everything classical computers can do and more. The implications for cryptography were immediate and severe. Encryption systems are designed around computational asymmetry. If quantum computers eliminate that asymmetry for certain problems, encryption collapses not because of poor design, but because the physical assumptions underlying computation have changed. Crucially, quantum mechanics does not need to be perfect to pose a threat. Cryptographic security relies on worst-case guarantees. Even a moderately powerful quantum computer, if capable of running specific algorithms, could undermine systems that protect trillions of dollars and billions of people. This realization transformed quantum computing from an academic curiosity into a strategic concern. Governments, intelligence agencies, and corporations began investing heavily in quantum research, not merely to build faster computers, but to understand the threat landscape. Yet quantum computing is extraordinarily difficult to realize physically. Qubits are fragile. They decohere when exposed to noise, temperature fluctuations, or electromagnetic interference. Maintaining quantum coherence long enough to perform useful computation requires extreme engineering precision. For years, these challenges led many to dismiss quantum computing as impractical. But progress continued. Experimental demonstrations of quantum logic gates improved. Error correction schemes were developed. Coherence times increased. Systems scaled from a handful of qubits to dozens, then hundreds. What matters is not whether quantum computers can yet break encryption, but whether the path to that capability is scientifically plausible. And by every credible measure, it is. This section reveals a critical truth. The threat to internet security does not come from hackers becoming smarter. It comes from physics allowing computation to escape classical limits. Quantum mechanics does not attack encryption directly. It undermines the assumption that certain problems are hard. Once that assumption fails, cryptography loses its foundation. In the next section, the documentary will confront the most misunderstood elements of quantum computing: the qubit, superposition, and entanglement, not as buzzwords, but as precise mechanisms that make cryptographic collapse possible. Section 3: Qubits, Superposition, and Entanglement, explained without hype. Why quantum information is powerful, fragile, and fundamentally alien to classical logic. By this point in the documentary, the threat is no longer abstract. Classical cryptography depends on assumptions about computation, and quantum mechanics permits a fundamentally different kind of computation. But the real danger and the real misunderstanding lies in how quantum information actually works. Section 3 strips away metaphor and marketing to reveal what qubits, superposition, and entanglement truly are, and why they matter. The basic unit of classical information is the bit. It exists in one of two mutually exclusive states: 0 or 1. Every classical computer, no matter how advanced, reduces all operations to sequences of these binary states. This constraint defines the limits of classical computation. A quantum computer replaces the bit with a quantum bit, or qubit. A qubit is not simply a faster bit, nor is it a bit that holds multiple values simultaneously in an I-graph a letter 2C6BE sense. A qubit is a physical system such as an electron spin, a photon's polarization, or a superconducting current loop that can exist in a quantum superposition of states. Mathematically, a qubit is described by a vector in a two-dimensional complex Hilbert space. Its state is a linear combination of 0 circumflex, y copyright and 1 circumflex, y copyright, each weighted by a complex amplitude. These amplitudes encode probabilities, but also phase information, which is essential for interference. The qubit does not contain both values in a classical sense. Instead, it exists in a state that cannot be described by classical probability alone. This distinction is critical. Superposition is not parallel classical computation. A qubit does not independently evaluate both 0 and 1. It exists in a state that collapses probabilistically when measured, yielding a single outcome. The power of quantum computation arises not from measurement, but from manipulating superpositions before measurement. Quantum gates operate on qubits by rotating their state vectors through Hilbert space. These operations are reversible and unitary, preserving probability amplitudes. Unlike classical logic gates, quantum gates do not discard information. They transform it coherently. When multiple qubits are combined, the system's state space grows exponentially. 2 qubits are described by 4 amplitudes, 3 qubits by 8, 10 qubits by over 1,000, and 50 qubits by more amplitudes than can be explicitly stored by any classical computer. This exponential scaling is the source of quantum computing's theoretical power and its practical difficulty. However, large state spaces alone do not yield useful computation. Without structure, a quantum system is just a cloud of probabilities. The key to harnessing this complexity lies in quantum interference. Interference allows probability amplitudes to add or cancel. By carefully designing quantum circuits, algorithms can be constructed so that incorrect solutions interfere destructively, while correct solutions interfere constructively. After measurement, the system collapses with high probability into the desired result. This is not brute force parallelism. It is guided wave manipulation. The most counterintuitive and most powerful feature of quantum information is entanglement. When qubits become entangled, their states can no longer be described independently. The system must be treated as a whole, regardless of spatial separation. Entanglement is not communication. No information is transmitted instantaneously. Instead, it creates correlations that exceed classical limits. These correlations allow quantum systems to encode relationships between variables in ways classical systems cannot. In computational terms, entanglement enables operations that depend on global properties of the system rather than local states. This is essential for algorithms that factor numbers, search large spaces, or simulate quantum systems themselves. But entanglement comes at a cost: fragility. Quantum states are exquisitely sensitive to their environment. Any interaction with the outside world, heat, electromagnetic noise, vibration, causes decoherence. Decoherence destroys superposition and entanglement, collapsing quantum behavior into classical noise. This is why quantum computers must be isolated, cooled to near absolute zero, and shielded from interference. It is also why scaling quantum systems is so difficult. Each additional qubit introduces new pathways for error. To combat this, researchers have developed quantum error correction. Unlike classical error correction, quantum error correction cannot simply copy information, because quantum states cannot be cloned. Instead, information is encoded non-locally across many physical qubits, allowing errors to be detected and corrected without measuring the underlying quantum state directly. This requires enormous overhead. A single logical qubit may require dozens or hundreds of physical qubits. This reality is often omitted in popular discussions, but it is central to understanding both the promise and the limits of quantum computing. Despite these challenges, experimental progress continues. Superconducting qubits, trapped ions, photonic systems, and topological qubits each represent different approaches, with different trade-offs in coherence time, gate fidelity, and scalability. No architecture has yet emerged as dominant, but all demonstrate the same fundamental principle: quantum information behaves differently from classical information. For cryptography, this difference is existential. Encryption algorithms are not protected by secrecy, they are protected by computational difficulty. Quantum algorithms exploit interference and entanglement to bypass that difficulty for specific problems. It is essential to emphasize again, quantum computers do not threaten all encryption. They threaten particular mathematical structures. Understanding which structures are vulnerable requires understanding how quantum algorithms operate on them. This is where abstraction ends and danger begins, because among the many quantum algorithms developed, one stands out not for its speed, but for what it breaks. In the mid-1990s, a single algorithm transformed quantum computing from theoretical curiosity into a cryptographic crisis. It demonstrated, with mathematical certainty, that a sufficiently powerful quantum computer could efficiently solve a problem once believed intractable. That algorithm did not rely on guessing keys, exploiting bugs, or brute force. It attacked the mathematical heart of encryption itself, and once it exists, no amount of secrecy can stop it. Section 4. The day encryption fails: how quantum computers actually break the internet. For decades, the modern internet has relied on a single assumption that almost no ordinary user ever thinks about: that certain mathematical problems are practically impossible to solve. Every secure email, every WhatsApp message, every bank transaction, every password you have ever typed into a website depends on this assumption. The security of the digital world is not protected by walls or weapons, but by time, specifically, the time it would take even the fastest classical computers on Earth to reverse encrypted data. Classical encryption does not make data unbreakable. It makes data too slow to break to be useful. Quantum computing threatens to erase that margin entirely. To understand how quantum computers break encryption, we must first understand how current encryption actually works at a fundamental level. Modern cryptography relies heavily on what mathematicians call one-way functions. These are operations that are easy to perform in one direction, but extraordinarily difficult to reverse without a secret key. One of the most important examples is prime factorization. Multiplying two large prime numbers together is computationally trivial, but given only the final number, determining which two primes were multiplied becomes exponentially harder as the number grows. This asymmetry is the backbone of RSA encryption, which has protected global communications for over 4 decades. When you visit a secure website, your browser and the server perform a cryptographic handshake. Public key encryption allows the server to publish a public key that anyone can see, while keeping a private key secret. The mathematics ensures that even if an attacker captures every bit of data being transmitted, they cannot reconstruct the private key in any reasonable time frame. On today's classical supercomputers, breaking a standard 2048-bit RSA key would take longer than the age of the universe. This has been the bedrock assumption of digital trust. Quantum computers shatter this assumption not by being faster in the traditional sense, but by being fundamentally different in how they process information. Classical computers operate in bits, ones and zeros. Quantum computers operate in qubits, which can exist in superpositions of states. This allows quantum systems to evaluate vast numbers of possibilities simultaneously. But the true cryptographic danger emerges when this quantum parallelism is combined with specific quantum algorithms designed to exploit mathematical structure. In 1994, mathematician Peter Shor published an algorithm that quietly changed the future of cybersecurity. Shor's algorithm demonstrated that a sufficiently powerful quantum computer could factor large integers exponentially faster than any known classical method. What would take classical machines billions of years could, in theory, be done by a quantum computer in hours or even minutes. This was not a hypothetical curiosity. It was a proof that the mathematical hardness protecting the internet was conditional, not absolute. The implications are staggering. RSA, Diffie-Hellman key exchange, and elliptic curve cryptography, all foundational to HTTPS, VPN, secure email, blockchain systems, and digital signatures, are vulnerable to Shor's algorithm. Once a quantum computer reaches a certain threshold of stability and scale, these systems do not degrade gradually. They collapse abruptly. Encryption does not weaken. It fails completely. What makes this threat uniquely dangerous is that it is retroactive. Encrypted data intercepted today can be stored indefinitely and decrypted later once quantum capabilities mature. This strategy is known as harvest now, decrypt later. Intelligence agencies, corporations, and adversarial states are already stockpiling encrypted communications with the expectation that future quantum machines will unlock them. This means that the moment quantum decryption becomes viable, Decades of historical secrets, diplomatic cables, military plans, medical records, financial archives could be exposed all at once. The risk extends far beyond governments. Digital identity itself is at stake. Digital signatures verify software updates, authenticate devices, and prove the integrity of documents. If quantum computers can forge digital signatures, malicious actors could impersonate trusted entities at a fundamental level. Fake software updates could be signed as legitimate. Fake financial transactions could appear authentic. Entire chains of digital trust would become indistinguishable from forgeries. Even cryptocurrencies are not immune. Blockchain systems rely on elliptic curve cryptography to secure wallets and verify transactions. A quantum attacker capable of deriving private keys from public addresses could drain wallets instantly. While some blockchain architectures could theoretically migrate to quantum-resistant algorithms, the transition is complex, slow, and vulnerable to coordination failures. The decentralization that makes blockchains resilient also makes rapid cryptographic upgrades difficult. Importantly, this is not merely a future problem. The migration to post-quantum cryptography must occur before large-scale quantum computers exist. Once quantum decryption becomes operational, it will already be too late to protect historical data. This creates a paradoxical security window. Defenses must be deployed years in advance of the threat, without knowing exactly when the threat will fully materialize. Researchers are developing quantum-resistant cryptographic systems based on mathematical problems believed to be hard even for quantum machines, such as lattice-based cryptography, hash-based signatures, and multivariate polynomial equations. However, these systems are newer, less battle-tested, and often computationally heavier. Deploying them globally requires updating protocols, hardware, firmware, and legacy systems across billions of devices, an effort comparable to rebuilding the internet while it is still running. The deeper concern is not just technical but philosophical. Encryption is what allows open societies to function in a digital world. It protects journalists, activists, businesses, and ordinary citizens from surveillance and manipulation. If encryption becomes temporarily or unevenly broken available only to states or corporations with quantum capabilities, the balance of power shifts dramatically. Information asymmetry becomes absolute. In this sense, quantum computing is not just a technological revolution. It is a geopolitical weapon. The first entities to achieve reliable, large-scale quantum decryption will gain unprecedented intelligence advantages. This has triggered what many experts now call the quantum arms race, where secrecy itself becomes a strategic asset. Nations are no longer racing merely to build faster computers, but to decide who controls the future of privacy. As Section 4 closes, one truth becomes unavoidable. The Internet was never designed to survive a world where its foundational mathematics could be reversed. Quantum computing does not attack the Internet from the outside, it breaks it from within, by invalidating the assumptions that made global digital trust possible in the first place. In the next section, we will examine whether this collapse is inevitable or whether quantum technology itself may paradoxically become the only tool capable of saving the Internet from its own quantum undoing. Section 5. Can quantum save the Internet? The rise of post-quantum cryptography and quantum defense. If quantum computing has the power to dismantle the cryptographic foundations of the Internet, then an unsettling paradox emerges. The same physics that threatens global digital security may also be the only force capable of preserving it. This is where the story becomes more complex, more uncertain, and far more urgent. The future of secure communication may depend not on stopping quantum computers but on learning how to defend against them using mathematics and physics that even quantum machines struggle to defeat. The first line of defense is not quantum at all. It is known as post-quantum cryptography. These are cryptographic systems designed to run on classical computers, yet remain secure even if the attacker possesses a powerful quantum computer. The idea is deceptively simple. Replace encryption methods that rely on problems quantum machines can solve efficiently, such as factoring and discrete logarithms, with problems that appear resistant to both classical and quantum attacks. One of the most promising approaches is lattice-based cryptography. Instead of relying on prime numbers, lattice cryptography uses high-dimensional geometric structures composed of points arranged in complex mathematical patterns. Certain problems in these lattices, such as finding the shortest vector, are believed to be extremely hard for both classical and quantum computers. Unlike RSA, these problems do not have known quantum shortcuts equivalent to Shor's algorithm. The security emerges not from number theory, but from geometric complexity. Another approach is hash-based cryptography, which relies on cryptographic hash functions algorithms that compress data into fixed-length outputs in a way that is irreversible and collision-resistant. Quantum computers offer only limited speedups against hash functions, meaning security can be preserved simply by increasing key sizes. Hash-based digital signatures are among the most conservative and well-understood post-quantum solutions, though they often come with trade-offs in signature size and performance. Multivariate cryptography, code-based cryptography, and isogeny-based cryptography represent other branches of post-quantum research, each with different assumptions, strengths, and vulnerabilities. What unites them is uncertainty. Unlike RSA and elliptic curve systems, which have been studied and attacked for decades, post-quantum algorithms are relatively young. Some candidates that initially appeared secure have already been broken through clever mathematical attacks, reminding researchers that cryptographic confidence is earned only over time. This uncertainty creates a dangerous balancing act. Migrate too slowly, and quantum attackers will arrive before defenses are ready. Migrate too quickly, and the internet could be locked into cryptographic systems that later turn out to be flawed. The challenge is compounded by scale. Billions of devices from smartphones and routers to industrial control systems and satellites must be updated, many of which were never designed to support cryptographic agility. But post-quantum cryptography is only half the story. The second line of defense is quantum itself, quantum key distribution, or QKD. Unlike classical encryption, which is based on mathematical assumptions, QKD relies directly on the laws of quantum physics. In a QKD system, encryption keys are transmitted using quantum states of particles, such as photons. Any attempt to intercept or measure these states unavoidably disturbs them, revealing the presence of an eavesdropper. This is not theoretical. QKD has been demonstrated in laboratories, deployed in limited commercial settings, and even tested via satellites. In theory, QKDO offers information-theoretic security protection that does not depend on computational difficulty at all. Even an infinitely powerful computer cannot break a key exchange through a perfect quantum channel without being detected. However, QKD is not a universal solution. It requires specialized hardware, secure endpoints, and physical infrastructure. It does not solve authentication on its own and must be combined with classical cryptographic systems. Distance limitations, cost, and integration challenges make it impractical for securing the entire internet in its current form. QKD is likely to protect critical links, government communications, financial backbones, and military systems rather than consumer traffic. This introduces a profound inequality risk. If only powerful institutions can afford quantum-secured channels, while the public internet relies on imperfect post-quantum algorithms, security becomes stratified. Privacy ceases to be universal and becomes a privilege. The question then is not just whether the internet can be saved but who it will be saved for. Meanwhile, global institutions are racing against time. Standards bodies are evaluating post-quantum algorithms, knowing that once selected, these standards will shape digital security for decades. Every decision must anticipate future advances in both quantum hardware and cryptanalysis. A single flawed assumption could compromise global trust at a planetary scale. The most unsettling reality is that no one knows when quantum computers will cross the threshold from experimental to existential. Progress is not linear. Breakthroughs in error correction, materials science, or quantum control could accelerate timelines dramatically. Conversely, unforeseen physical limits could slow development. This uncertainty forces the world to prepare for a threat that may arrive suddenly, without warning, and without the courtesy of gradual escalation. What emerges is a new security doctrine. In the classical era, encryption failures were localized and recoverable. In the quantum era, failures are systemic and irreversible. Once encrypted data is exposed, it cannot be unexposed. Once trust is broken at scale, rebuilding it may take generations. Section 5 therefore marks a turning point in the documentary's narrative. Quantum computing is no longer just a looming threat, it is a catalyst forcing humanity to rethink the meaning of secrecy, trust, and security in a universe governed by probabilistic laws. The internet was built on certainty, deterministic machines, predictable algorithms, and stable assumptions. Quantum mechanics introduces uncertainty at the deepest level of computation itself. In the next section, we will move beyond technology and examine the human dimension, the geopolitical race, ethical dilemmas, and power struggles that emerge when breaking encryption becomes a matter of national survival rather than academic curiosity. When ready, ask for Section 6, and I will continue with the same depth, continuity, and scientific rigor. Section 6. The quantum arms race, when encryption becomes a weapon of nations. Once it became clear that quantum computing could undermine the cryptographic foundations of the internet, the problem ceased to be purely scientific. It became geopolitical. Encryption, once a technical tool used quietly in the background of digital systems, transformed into a strategic asset comparable to nuclear technology, satellite surveillance, or missile defense. The question was no longer whether quantum computers could break encryption, but who would get there first, and what they would do with that advantage. In classical geopolitics, power has always followed information. The ability to intercept, decode, and exploit an adversary's communications has shaped wars, alliances, and empires. Quantum computing threatens to deliver the most asymmetric intelligence advantage in human history. A nation capable of silently decrypting global communications would not need to attack its rivals directly. It could anticipate decisions, manipulate markets, influence elections, and neutralize threats before they materialize. This is why quantum research is no longer transparent. Unlike early internet technologies, which emerged from open academic collaboration, quantum computing is increasingly classified. Governments fund national quantum initiatives under defense budgets, not science grants. Laboratories that once published freely now operate behind security clearances. The flow of knowledge is narrowing, not expanding. At the center of this race is the fear of a cryptographic surprise. Unlike conventional weapons, quantum capability cannot be easily observed. There are no missile tests, no visible deployments. A quantum computer powerful enough to break encryption could exist in secret, used covertly for years before its presence is detected. By the time the world realizes it exists, the damage may already be irreversible. This possibility has reshaped intelligence doctrine. Intelligence agencies now operate under the assumption that encrypted communication stored today may be decrypted tomorrow. This has led to a strategy known as harvest now, decrypt later. Vast quantities of encrypted data, diplomatic cables, corporate secrets, personal communications are being intercepted and archived, not because they can be read today, but because they might be readable in the future. This fundamentally alters the meaning of privacy. In the classical world, encryption offered a temporal guarantee. If data remained secure long enough, it lost strategic value. In the quantum era, time becomes an enemy. Every encrypted message sent today is a potential liability decades from now. The past is no longer safe. The arms race is not just about building quantum computers, but about controlling the entire ecosystem. Materials, fabrication facilities, cryogenic infrastructure, error correction techniques, and quantum software. Unlike classical computing, quantum systems are fragile, expensive, and deeply tied to physical constraints. This makes supply chains strategically sensitive. Superconducting materials, ultra-pure silicon, rare isotopes, and specialized lasers become national security resources. As competition intensifies, cooperation erodes. International research collaborations fracture along political lines. Talent mobility becomes restricted. Scientists face ethical dilemmas, publish discoveries openly and risk empowering adversaries, or remain silent and slow global progress. Knowledge itself becomes weaponized. There is also a destabilizing feedback loop. If one nation suspects another is close to achieving cryptographically relevant quantum computing, it may accelerate offensive cyber operations preemptively, before its own communications become vulnerable. This creates a digital version of the security dilemma. Defensive preparations by one actor are perceived as offensive threats by others. Unlike nuclear weapons, quantum computers do not create immediate physical destruction. Their impact is subtle, systemic, and cumulative. Financial systems can be manipulated quietly. Supply chains can be disrupted invisibly. Military decisions can be anticipated and countered without firing a single shot. This ambiguity lowers the threshold for use, making quantum-enabled cyber operations more likely, not less. The risk is compounded by inequality between nations. Quantum technology requires immense capital, infrastructure, and expertise. Only a handful of countries can realistically compete at the highest level. This creates a new digital divide not between individuals, but between civilizations. States without quantum capabilities may find their sovereignty eroded, their economic systems exposed, and their political processes vulnerable. Even alliances become fragile. Sharing intelligence has always required trust, but quantum asymmetry could undermine that trust entirely. If one ally secretly possesses superior decryption capabilities, information sharing becomes a liability rather than a benefit. The architecture of international cooperation begins to fracture under suspicion. This section also forces a deeper question. Can deterrence exist in the quantum era? Nuclear deterrence relies on visibility and mutual vulnerability. Quantum deterrence relies on secrecy and uncertainty. No one can prove what they can or cannot decrypt. This opacity destabilizes traditional balance of power models. As a result, policymakers face an unprecedented challenge. They must regulate a technology they do not fully understand, moving at a pace faster than legal frameworks can adapt. Export controls, research restrictions, and ethical guidelines struggle to keep up with scientific progress. Every decision risks either falling behind or escalating conflict. By the end of Section 6, one reality becomes unavoidable. Quantum computing is not merely a technological breakthrough. It is a geopolitical force that reshapes power itself. Control over information has always defined civilizations, but quantum mechanics threatens to rewrite the rules entirely. The Internet was built on openness, trust, and shared standards. The quantum arms race pushes the world towards secrecy, fragmentation, and digital nationalism. Whether this transition can be managed peacefully or whether it leads to systemic instability remains unresolved. In the next section, we will move from nations to corporations and individuals, exploring how quantum threats ripple into economies, personal identities, and everyday digital life. When ready, ask for Section 7, and the documentary will continue seamlessly. Section 7. When quantum breaks the economy, money, identity, and trust in a post-encryption world. The geopolitical consequences of quantum computing are immense, but their effects do not remain confined to governments and intelligence agencies. They cascade outward, infiltrating the global economy, corporate infrastructure, and the most intimate digital spaces of individual lives. At its core, modern civilization is an information system. Money, identity, contracts, ownership, and reputation exist not as physical objects, but as cryptographically secured records. When encryption weakens, reality itself becomes negotiable. The global financial system is built on cryptographic trust. Every bank transfer, stock trade, credit card payment, and interbank settlement depends on digital signatures and encrypted channels. These systems assume that forging a transaction is computationally infeasible. Quantum computing directly challenges that assumption. If cryptographic keys can be extracted or signatures forged, the concept of financial finality collapses. A transaction is no longer unquestionably valid simply because it has been cryptographically signed. The immediate danger is not that quantum computers will empty bank accounts overnight, but that confidence in the system will erode. Markets are not just mechanisms. They are collective beliefs. If investors suspect that records can be altered retroactively, or that private financial data is exposed, volatility increases. Trust evaporates faster than capital. Liquidity dries up not because funds disappear, but because participants refuse to move them. Digital currencies illustrate this vulnerability with stark clarity. Cryptocurrencies rely almost entirely on cryptographic primitives for security. Private keys define ownership. Digital signatures authorize transfers. Quantum attacks that compromise these primitives could allow attackers to impersonate legitimate owners or reconstruct private keys from public information. Entire blockchain histories could become suspect not because they are rewritten, but because their cryptographic foundations no longer guarantee authenticity. Even systems designed to be decentralized are not immune. Consensus mechanisms assume that cryptographic identities are unforgeable. If that assumption fails, decentralization offers little protection. The promise of trustless systems collapses when trust in mathematics itself is undermined. Beyond finance lies digital identity. Passports, biometric databases, health records, employment credentials, and access controls all rely on encryption to protect authenticity and confidentiality. In a post-quantum world, identity theft is no longer a matter of stolen passwords, but of reconstructed identities. An attacker does not need to guess who you are. They can mathematically derive your digital presence. This creates a psychological crisis as much as a technical one. Modern identity is persistent, portable, and cumulative. Once compromised, it cannot be easily reset. You can change a password, but you cannot change your medical history, your genetic data, or your digital past. Quantum-enabled breaches would not be temporary disruptions, they would be permanent fractures. Corporations face an existential dilemma. Intellectual property designs, formulas, algorithms, trade secrets is the lifeblood of modern industry. These assets are stored, transmitted, and protected digitally. If encryption fails, competitive advantage becomes ephemeral. The incentive to innovate diminishes when secrets cannot be kept. The balance between openness and protection tilts dangerously toward secrecy or stagnation. Supply chains amplify the risk. Modern production depends on interconnected digital systems spanning continents. A cryptographic failure in one link propagates through the entire chain. Contracts become disputable. Provenance becomes uncertain. Accountability dissolves into ambiguity. There is also an asymmetry of preparedness. Large corporations may afford post-quantum migration, hardware upgrades, and cryptographic audits. Small businesses, nonprofits, and individuals cannot. This creates a security class system where resilience correlates with wealth. Economic inequality becomes encoded into the infrastructure of trust itself. Insurance markets already struggle to price cyber risk. Quantum uncertainty makes actuarial modeling nearly impossible. How do you insure against a threat whose arrival time is unknown, whose impact is systemic, and whose detection may come only after damage is done? As insurers retreat, risk shifts directly onto individuals and governments. Social trust is the final casualty. The internet functions because users assume that communications are authentic, transactions are binding, and records are accurate. When these assumptions erode, suspicion replaces confidence. Every digital interaction becomes provisional. The cost of verification skyrockets, slowing commerce, collaboration, and creativity. The deeper issue is philosophical. Modern society outsourced trust to mathematics. We believed that algorithms could provide objective security, independent of human institutions. Quantum computing exposes the fragility of that belief. Mathematics itself is not broken, but our assumptions about its permanence are. Section 7 reveals that the quantum threat is not abstract or distant. It reaches into wallets, identities, and relationships. It challenges the very idea of a shared digital reality. The internet, once a tool for connection and empowerment, risks becoming a space of uncertainty and latent betrayal. In the next section, we will confront the hardest question yet. Can society adapt fast enough, and what happens if it cannot? Section 8. Racing the clock. Can society transition before quantum collapse? Technological revolutions do not fail societies because they arrive. They fail societies because they arrive faster than adaptation allows. Quantum computing presents precisely this danger. Unlike previous computational advances, which scaled gradually and predictably, quantum progress is nonlinear, opaque, and driven by breakthroughs that cannot be scheduled. Society is attempting to redesign the cryptographic foundation of civilization while standing on it. The transition to quantum-resistant systems is not a single upgrade. It is a multi-decade migration touching every layer of the digital stack. Hardware, firmware, operating systems, protocols, applications, and human processes must all change in coordination. History offers no precedent for a security transition of this magnitude occurring under time pressure and uncertainty. At the protocol level, Internet standards were designed for stability, not agility. Cryptographic primitives are deeply embedded in protocols like TLS, ISEC, SSH, and digital certificate infrastructures. Replacing them requires compatibility across billions of devices. Any misalignment risks fragmentation. Parts of the internet that cannot securely communicate with others. Legacy systems are the most vulnerable. Industrial control systems, medical devices, satellites, and infrastructure hardware often run on software that cannot be easily updated, if at all. These systems were built with decades-long lifespans and minimal security assumptions. Quantum vulnerability transforms them into permanent weak points, digital fossils embedded in critical infrastructure. Human institutions compound the difficulty. Governments move slowly by design. Regulation requires consensus, debate, and enforcement. Yet quantum timelines do not respect legislative calendars. A cryptographic standard approved today may be obsolete tomorrow. Bureaucratic inertia becomes a security risk. Education is another bottleneck. There are not enough cryptographers, quantum engineers, or security architects to execute a global transition at speed. Training new experts takes years. Meanwhile, attackers need only one successful exploit to cause disproportionate damage. Corporate incentives are misaligned. Investing in post-quantum security yields no immediate revenue and offers protection against a threat that may seem abstract or distant. Short-term financial pressures discourage long-term resilience. By the time quantum risk becomes undeniable, retrofitting systems may be prohibitively expensive or technically impossible. This creates a classic coordination problem. Each actor waits for others to move first. Governments wait for standards. Corporations wait for regulation. Individuals wait for products. Meanwhile, encrypted data continues to accumulate, harvested, stored, and waiting for decryption. The danger is not a sudden collapse, but a silent one. Trust degrades gradually. Security incidents become harder to attribute. Confidence erodes unevenly. By the time society recognizes the depth of the problem, the informational damage may already be irreversible. Yet adaptation is not impossible. Cryptographic agility systems designed to swap algorithms without redesign offers a partial solution. Hybrid encryption schemes combine classical and post-quantum algorithms, buying time while uncertainty remains. Decentralized identity models reduce single points of failure. Zero-trust architectures assume breach rather than prevent it. But these solutions require a cultural shift. Security must be treated as infrastructure, not a feature. Resilience must be valued over efficiency. Redundancy must be accepted as necessary, not wasteful. Section 8 exposes the central tension of the quantum era. Physics advances faster than governance, and mathematics evolves faster than institutions. Whether society can close this gap is not a technical question alone, it is a test of collective foresight. In the next section, we will look beyond mitigation and ask a deeper question: what happens if quantum computing changes not just security, but the very meaning of computation and knowledge? Section 9. Beyond security, how quantum computing rewrites what can be known. Up to this point, quantum computing has been framed as a threat to encryption, economies, and institutions. But this framing, while urgent, is incomplete. Quantum computing does not merely challenge existing systems, it challenges the conceptual boundaries of computation itself. It forces humanity to confront a deeper question: what are the limits of knowledge in a universe governed by quantum mechanics? Classical computation rests on determinism. Given sufficient time and resources, any computable problem can, in principle, be solved. Cryptography exploited this by choosing problems that were impractical to solve within the age of the universe. Quantum computing disrupts this balance not by making all problems easy, but by reshaping which problems are hard. The distinction between feasible and infeasible shifts in ways that are not intuitive, predictable, or evenly distributed. This shift reveals a profound asymmetry. Some problems that appear intractable to classical machines become efficiently solvable by quantum algorithms, while others remain stubbornly resistant. This is not a simple acceleration, it is a reclassification of reality's computational landscape. Encryption breaks not because physics betrays us, but because we misunderstood which mathematical structures are stable under quantum evolution. Quantum algorithms exploit superposition and interference to amplify correct answers and cancel incorrect ones. This process is not transparent. Unlike classical computation, where intermediate states can be inspected and verified, quantum computation hides its reasoning in probability amplitudes. The answer emerges statistically, not narratively. This raises a subtle epistemological challenge. We may know the result is correct without fully understanding why. As quantum systems scale, verification becomes a central problem. How do you confirm the output of a quantum computer when no classical machine can replicate the calculation? This issue extends beyond cryptography into chemistry, materials science, climate modeling, and fundamental physics. Quantum computers promise insights into systems so complex that human intuition fails, but trusting those insights requires new standards of evidence and confidence. In this sense, quantum computing does not just threaten secrecy, it transforms authority. Knowledge becomes asymmetric. Those who control quantum resources gain access to predictions and optimizations unavailable to others. This asymmetry is not merely economic or political, it is cognitive. Decision-making power shifts toward entities capable of computing beyond classical limits. This introduces a paradox. Quantum mechanics is inherently probabilistic, yet quantum computation can yield more precise predictions for complex systems than any classical method. The universe becomes more predictable and less interpretable at the same time. We gain control while losing explanation. The implications ripple outward. Scientific discovery accelerates, but peer review struggles to keep pace. Models become too complex to audit fully. Trust shifts from transparency to reputation and institutional credibility. The risk of error or manipulation grows, as fewer actors can independently verify results. There is also a boundary question. Not all problems succumb to quantum advantage. Some are believed to be hard even for quantum machines. These hard problems form the new bedrock of security and uncertainty. Identifying them is one of the most critical scientific challenges of the century. A single unexpected algorithm could collapse assumptions across multiple domains. Section 9 reveals that the quantum revolution is not solely about faster computers or broken encryption. It is about a reordering of epistemic power: who knows what, who can prove it, and who must trust without understanding. The internet, finance, and governance are merely the first domains to feel this shift. In the final section, we will confront the ultimate question: whether humanity can coexist with a technology that outpaces not just institutions, but comprehension itself.